Bismillahirrahmanirrahim. Welcome to my YouTube channel Calculus and Mathematics Learning. In the previous two videos, I solved past 20 questions of exercise number 8.2 relevant with the chapter number 8 Eigenvalue, Eigenvector and Diagonalization. So in today's video, I will solve the questions from question number 23 up to question number 30 or 40. So let's move toward question number 23, exercise number 8.2, lecture number 11, BS Linear Algebra by Bernold, Kolman and David R. Hill, 8th edition. Chapter name is Eigenvalues, Eigenvector and Diagonalization. So question number 23 tells that let A be a 2 cross 2 matrix whose eigenvalues are 3 and 4 and associated eigenvectors are -1, 1 and 2, 1 respectively. Without computation, find a diagonal matrix D that is similar to matrix A and non-singular matrix P such that P inverse AP is equal to D. So in this question, we are needed to find the diagonal matrix D and a non-singular matrix P. So the non-singular matrix P can be found out directly from these two eigenvectors -1, 1 and 2, 1. These are actually our given matrix P. After this, we will find the inverse of this matrix by using one word determinant of P into adjoint of P. So adjoint of this matrix will be 1 minus 2 minus 1 minus 1 and the determinant of this matrix will be -3 from over here. So after this, we need the value of the diagonal matrix D. So the diagonal matrix D will be equal to, remember, in the diagonal matrix, on the diagonal entries we will have eigenvalues and the non-diagonal entries should be 0. So lambda 1 is the first entry, which is actually the first eigenvalue 3. So over here put 3, and the lambda 2 is the second second entries, which is actually 4, and the non-diagonal entry will comes down as it is. It means the diagonal matrix D is equal to 3, 0 and 4. So this is the required diagonal matrix D and this is the required matrix P. Now move to the next question, question number 24. Let A be a 3 cross 3 matrix whose eigenvalues are -3, 4 and 4 and associated eigenvectors are -1, 0, 1, 0, 0, 1 and 0, 1, 1 respectively. Without computation, find a diagonal matrix D that is similar to the matrix A and non-singular matrix P such that P inverse AP is equal to the diagonal matrix D. So the solution to this question number 24 is similar to the solution of question number 23, which is actually the previous question. So in the previous questions, we were given with the matrix whose order were 3 cross 3, but in this question the order of the matrix is 3 cross 3 matrix given. So over here eigenvectors are given -1, 0, 1, 0, 0, 1 and 0, 1, 1. So the required non-singular matrix P will be actually x1, x2, x3. x1 is the first eigenvector -1, 0, 1, x2 is the second eigenvector 0, 0, 1 and x3 is the third eigenvector 0, 1, 1. This is the required non-singular matrix P. And the diagonal matrix D will be actually on the main diagonal the eigenvalues will lie and the non-diagonal entries should be 0. So lambda 1 is the first eigenvalue -3. Lambda 2 is the second eigenvalue 4 and lambda 3 is the third eigenvalue 4. So this is actually the required diagonal matrix D. Now move towards question number 25. They tells that from question number 25 to 28, find two matrices that are similar to the matrix A. So question number 25, a matrix is given A is equal to 3, 4, 0, 0. Remember the condition for the matrices that are similar to the given matrix A will be the first condition that the determinant of this matrix given matrix and the similar matrices should be same. Over here the determinant of this matrix is actually 3 into 0 gives us 0 and -4 into 0 gives us 0. So the determinant of this matrix is 0. Second condition is this. First condition determinant will be 0. Second condition is this, that the eigenvalues of both the similar matrices and the given matrices should be same. Eigenvalues should be same. And the third condition is eigenvector should be same. So over here the given matrix is triangular matrix. So for a triangular matrix the eigenvalues actually lies on the main diagonal. So over here the eigenvalues lambda 1 and lambda 2 is 3 and 0. So from over here, I generate a matrix just like B is equal to, I write a matrix just like 3, 0, 0 and 0. So over here on the main diagonal, the eigenvalues lies with 3, 0 and the non-diagonal entries is 0. So over here the determinant of this matrix is 0. And also the eigenvalues are 3, 0 and the eigenvector will also be satisfied. So let's suppose this is the first similar matrix and I consider another matrix. I rearrange and replace and flip these two values, so it becomes 0, 3, 0, 0. So determinant of this matrix is also 0 and the eigenvalue also lies on the main diagonal. So these are the required two similar matrices similar to the given matrix A. Now move toward question number 26. So first of all, I find out the required eigenvalue by using the definition f of lambda is equal to determinant into lambda I2. I2 is 1, 0, 0, 1 minus given matrix which is 1, 2, 3, 0. So it becomes determinant of lambda into 1 minus 1, lambda minus 1, lambda 0 minus 2 minus 2, 0 minus 3, lambda and minus 0. So by expanding it becomes lambda square minus lambda minus 6. So lambda square minus lambda and minus 6 f of lambda. Now finding the values of lambda, so it becomes lambda square minus 3 lambda plus 2 lambda minus 6, 0. So it becomes lambda into lambda minus 3 plus 2 into lambda minus 3 is equal to 0. So it will give us lambda is equal to minus 2 and 3. As the given values of lambda are distinct, it means the given matrix is diagonalizable. So we can easily find out the similar matrices. Now over here past finding the determinant. So determinant 1 into 0 gives us 0 minus 2 into 3 will give us 6. So the determinant of this matrix is minus 6. Now on the diagonal, the eigenvalue will lie past condition minus 2, 3. Let's suppose this is matrix P and the determinant of this matrix should be 0, minus 6. So let's suppose I write it just like this. So determinant of this matrix is minus 6. And also on the main diagonal the eigenvalue lies, this is, let's suppose first similar matrix, I consider another matrix, flip these two values, so 3 minus 2 and these value will come down as it is. This is the another similar matrix. So these are the required two similar matrices to the given matrix A. Now move to the next question, our question number 27. A is equal to 2, 0, 0, 1, 1, 0 minus 1, 0, 1. So this matrix is actually a triangular matrix, lower triangular matrix, because the entries above this main diagonal is 0. It means this matrix is lower triangular matrix. The second thing is the determinant of this matrix is 2. So it means the required similar matrices determinant should be 2. So over here on the main diagonal, the values of lambda 1, lambda 2, lambda 3, these are the eigenvalue which is 1, 1, 2, these diagonal entries. So in the required similar matrices, the diagonal entries should be 1, 2, 1. Means it will lie from these three values 1, 1, 2. So 1, 2, 1 and 1, 1, 2. And the second thing is the determinant of these matrices is also 2. It means these are the required two similar matrices. 1, 0, 0, 1, 2, 0 minus 1, 0, 1, 1, 0, 0, 1, 1, 0 minus 1, 0, 2. Determinant of these matrices is 2 and also the eigenvalue lies on the main diagonal of these two similar matrices. Move to our question number 28. A is equal to 2, 0, 0, 1, 2, 1, 0, 1, 2. So first of all, use the definition f of lambda is equal to determinant into lambda I3 minus A. So it will give us this. Now taking the determinant and by expanding with row 1, it will give us the values of lambda 1, 2, 3. It means the eigenvalues lies on the main diagonal of the similar matrices should be 1, 2, 3. So in the required similar matrices, on the main diagonal we have 1, 2, 3 and 1, 3, 2. Second thing, the determinant of the given matrix is 6. It means the required determinant of the required similar matrices should be 6. So the determinant of this matrix is 6 and determinant of this matrix is also 6. And the eigenvalue lies on the main diagonal 1, 3, 2, 1, 2, 3. So from over here the eigenvalues are 3. So we will write their permutation 3 factorial. So it means 3 factorial is equal to 6. So 6 different type of arrangement is possible of these main diagonal values with actually eigenvalue. It gives us 6 different type of similar matrices. So these are the required two similar matrices to the given matrix A. Now move toward question number 29. That tells that from question number 29 to 32 determine whether the given matrix is similar to a diagonal matrix. Question number 29, a matrix is given 2, 3, 0, 0, 1, 0, 0, 0, 2. So first of all, this matrix is actually upper triangular matrix because the entries above this main diagonal below main diagonal entries is 0. It means this is upper triangular matrix. So the eigenvalue will actually their main diagonal 1, 2 and 2. Over here repetition comes. The main eigenvalues is repeated. It means the theorem is failed. We will proceed to the next theorem. Ax is equal to lambda x. So take out x common. We left with lambda I3 minus a. So first put lambda 2. So 2i3 minus a. So 2 into i3 minus a is this matrix. It will give us this into xyz. Xyz is actually x1 is equal to 0. So over here y is 0. So from over here y is 0. Now I do not have given with the value of x and z. So let's suppose I consider x is equal to arbitrary constant t and z is equal to arbitrary constant r. So two condition is given over here. X1 is equal to xyz. So first put r is equal to 0, t is equal to 1. It will give us 1, 0, 0. x2 is equal to xyz. Put r is equal to 1, t is equal to 0. It gives us another eigenvector x2. So two eigenvector is generated by putting lambda 1 in the same equation x2 into lambda I3. So lambda is 1, so I3 minus a is equal to 0. It will give us this coefficient matrix minus 1 minus 3 0 0 0 0 0 0 minus 1. So from over here z is 0. From over here minus x minus 3y will be equal to 0. Let's suppose I consider y is equal to r. So it becomes x is equal to negative 3r. So x3 is xyz. X is minus 3r, y is rz0. Put r1, it gives us minus 3 1 0. So three linearly independent eigenvector is generated. It means the given matrix is diagonalizable. So the given diagonal matrix will be 2 1 2 0 0 0 0 0. From over here the determinant of this matrix is 6 and the determinant of this diagonal matrix is also 6. It means that the diagonal matrix is possible. For question number 30, 2 3 1 0 1 0 0 0 30. The eigenvalue will be main diagonal because this is upper triangular matrix. So x into 2 lambda I3 minus a. So first put lambda 2. It will give us one eigenvector. Then put lambda 1, so it will give us another eigenvector. So just two eigenvector is generated. Remember, the given matrix is 3 cross 3 order matrix, not 2 cross 2 order matrix. So we need 3 eigenvector, not 2 eigenvector. It means this matrix is not diagonalizable. So if this is not diagonalizable, we cannot find a diagonal matrix. So it means the diagonal matrix is not possible to the question number 30 to this matrix A. Now move toward question number 31, minus 3, 0, 1, 2. This matrix is actually lower triangular matrix because the entries above this main diagonal is 0. So this is actually a lower triangular matrix. So the eigenvalue will be actually the main diagonal value because of this triangular matrix. So the eigenvalue will be minus 3 and 2. As the eigenvalue are distinct and different, it means given matrix is diagonalizable. So it means the diagonal matrix is possible to this matrix. So remember the determinant of this matrix is minus 6 and the eigenvalue is minus 3 2. So the diagonal matrix will be minus 3 2 0 0 because the determinant of this matrix is minus 6, one condition, and also for the diagonal matrix the non-diagonal entries will be 0, and also the similar matrix is possible to this matrix. Move toward question number 32, 1 1 0 2 2 0 3 3 3. So first using definition, f of lambda is equal to determinant into lambda I3 minus a. By simplification, it will give us this matrix, taking the determinant and expanding with the column 3. So for lambda minus 3, I cross this row and this column. So expanding with C3, this and this will give us 0. So left with lambda minus 3. So for lambda minus 3 cross this row and this column, we left with lambda minus 1, minus 1 minus 2, lambda minus 2. Taking the determinant of this, it becomes lambda minus 1 into lambda minus 2, and from over here we get minus 2. So by further simplification inside the square bracket, we get lambda square minus 3 lambda. These are cancelled with each other. So from over here, take out lambda common. So we left with lambda minus 3, and this lambda minus 3 come down as it is. So we get 3 solutions, 0 3 3. So the roots are repeated, so the theorem fail. And move to the next theorem, x into lambda I3 minus a. First put lambda 3. It will give us 2 eigenvector because over here 2 linearly arbitrary constant is generated t and r. It will give us 2 eigenvector, and by putting 0 over here it become x2 into negative a. It will give us another eigenvector. So 3 linearly independent eigenvector is generated. It means the given matrix is diagonalizable, and So the diagonal matrix to this question number 32 to this matrix is possible. Let's suppose this is the diagonal matrix. So in this diagonal matrix, the non-diagonal entries should be 0, and on the main diagonal, this eigenvalue will lie. So this is actually the diagonal matrix, and also the similar matrices is possible to this matrix. Now move toward the question number 33. That tells that from question number 33 to 36 show that each matrix is diagonalizable and find a diagonal matrix similar to the given matrix. So question number 33, matrix is 4, 2, 3, 3. Determinant of this matrix is 6. So because 4 into 3, 12, 12 minus 6 gives us 6. Move to solution. F of lambda is equal to determinant into lambda identity matrix minus original matrix gives us this matrix. By expanding the determinant, it will give us lambda square minus lambda minus 6 lambda plus 6. By simplification, it will give us lambda minus 1 lambda minus 6. From over here we get two values of lambda. Lambda is equal to 1 and 6. So since the roots are distinct, it means the given matrix is diagonalizable according to the given theorem. So the required diagonal matrix will be, now 1, 6 is actually the eigenvalue. In the diagonal matrix, it will lie along the diagonal. So in the along the diagonal, we can write either 1, 6, or we can also write it just like 6, 1 by flipping this 1 and 6, and the non-diagonal entries will be 0. So this is actually the required diagonal matrix. The determinant of this matrix is 6, and the determinant of the given matrix is also 6. It means that this diagonal matrix is similar to the given matrix. Move to 34. 3, 2, 6, 4. So using definition, f of lambda is equal to determinant into lambda identity matrix gives us this minus original matrix. By simplification, it gives us this. Now by expanding this for the determinant, it will give us lambda square minus 7 lambda plus 12 minus 12. They cancel with each other because these are the determinants of each other. We left with lambda square minus 7 lambda. It will give us two lambda values of lambda. Lambda is equal to 0 and 7. Now determinant of the given matrix is 0 because 3 into 4 12 and minus 6 into 2 gives us 12, so it gives us 0. So over here 0 and 7 are the eigenvalue, so it will lie along the diagonal. We can write it either 0, 7, or by flipping it, it will give us 7, 0. So we can write it either in this form or either in this form. And the non-diagonal entries should be 0. So the determinant of this matrix is 0, determinant of this matrix 0, and determinant of the given matrix is also 0. So determinant of both the matrix is 0. It means that the given matrix is similar to this diagonal matrix. Move toward question number 35. 2 minus 2, 3, 0, 3 minus 2, 0 minus 1, 2. So if of lambda is equal to determinant into lambda into identity matrix gives us this minus original matrix. By simplification, it gives us this. Expand with column 1. So for lambda minus 2, cross this row and this column, and taking the determinant of these. So lambda minus 3 into lambda minus 2 and minus 2. By simplification, it will give us three distinct values of lambda 1, 2 and 4. So if the lambda values are distinct, it means the given matrix is diagonalizable. So the diagonal matrix will be, now the eigenvalue are 1, 2, 4. So in the diagonal matrix, these eigenvalue will lie along the diagonal. So over here 3 eigenvalue is generated, so it will be 3 factorial. So it means 6 possible arrangement is possible for the diagonal matrix. 1, 2, 4 or 2, 1, 4 or 1, 4, 2 or 1, 2, 4, or either replace this 2 value. So 6 different type of diagonal matrix is possible. The determinant of this matrix is 8, and the determinant of the given original matrix is also 8. It means this matrix is similar to the given matrix.